to base D2. And sometimes this base D2 is 2, then we call the number binary number. And there were some questions about the binary numbers and bits. Binary numbers are actual numbers. For instance, 11.11 with base 2 is a real number. If you use decimal representation, it means 1 times 2 to the power of 1 plus 1 times 2 to the power of 0 plus 1 times 2 to the power of negative 1 plus 1 times 2 to the power of negative 2, and then it is 3.75. So it's actual number. Then what is bits? Bit could be defined anyway. Bit could be defined exactly the same way, like this one, or we may define differently. So this is the difference. There is a similarity and the difference. So you should know the similarity and the difference. As numbers, this is the exact number. There is no other interpretation of this one. But sometimes this can be directly converted to bits. But sometimes this can be defined differently. That's the similarity and the difference, right? Sometimes we exactly define bits the same way as binary numbers. Sometimes we don't. So binary numbers are numbers. So there is no other interpretation than this one. So it is exactly this one. Always it is exactly this one. Bit, you may define any way you want. Bits, you may define any way you want. Sometimes you can define the same way. Sometimes you may say any different way. So you should see the similarity and difference clearly. So I received a lot of email questions about the similarity and difference. So similarity is just using 0 and 1 is similarity, right? Using 0 and a similarity. Difference, this is clearly defined this way, right? There is no other interpretation than this interpretation. Bits, you may define any way you want. Is this clear enough? And one more answer is this one. I asked you, in homework 2, I asked you to convert real number with D1 to either binary or D2, right? So I asked you to convert D1 to binary or D2. And in homework 3, I asked you to convert the real number, right? Real number usually is 10, to binary numbers in IEEE right? I mean 4. So I don't know the exact, I cannot remember the exact number, but something like this. Then what's the difference and the similarity? Here it is actual number. For instance, 3.75 is the actual number with base 10. Then it can be converted to 11.11. This is what I wanted, right? This is what I wanted. Here, I asked to convert a real number to bit representation, but this bit representation is not binary number. So this is different, right? These are different. It's a binary number. This is bit representation. So you should not say, oh, because of this, it should have 1111. No. No. So you should have this kind of representation. 1111 in binary number is equal to 1 times 1.111 with binary number times 2 to the power of 1. Then in binary number representation, we use sign bit, right? Because we have plus sign bit. And then power is 1. Power 1 is written this way, right? Power 1 is written this way. And then this number with normalized, we get 1, 1, 1, 1, and then 0 everywhere. So this is the one that you should do in homework 3. So you should know the similarity and the difference. Intermediate results require this kind of conversion, but it's not the goal. Our goal is finding bits like this. And the final problem is this one. So there are 3 problems in homework 3. In homework 3, doing this thing from real number to bits like this, right? This is the problem number 1 or 2, and the other. So there are 2 problems, right? From bits to numbers, from numbers to bits. So there are 2 problems like this. And finally, the range of the number. So I will pause and then go up and then write the situation. The range of the number is this. Other than 0 and infinity, right? Other than 0 and infinity, there are positive numbers that you can define, right? Positive numbers here and then here. So there are some numbers, and then we want to find the minimum number and the maximal number that you can define. Then the minimum number is what? And maximum number is what? And mathematically we can represent these things like this. This is usually denormalized term, so 0.00 all the way up to the final one is 1, right? This can be written and then multiplied by 2 to the power of 1 minus bias bit. So this is the smallest number that we can represent, right? And then the biggest number that we can represent is 1.1111 everywhere, right? And then this one is already assumed, and then this number of bits, right? Multiplied by 2 to the power of the maximal number. In fact, this number is equal to by. So once we write it this way, then we can extract the power. This is also 2 to the power of something, right? And then this is also 2 to the power of something. Then from this, we can get 2 to the power of some possible power, right? And then this also can be written this way. It can be written this way. It is very close to, right? 2 minus the last number. If we add the last number, then by carry over all the way up to, it becomes 2. So if we add very small number like 0.000001 here, then it will become 2. In other words, this number is 2 minus this number, right? 2 minus this number. 2 minus 0.000001. Or, if we write it in power form, 2 minus 2 to the power of these many bits, right? So the number of bits. So this is the number that we can represent. And then 2 to the power of max, right? 2 to the power of usually bias. So what I want to see is this one. When you run the range function with number of exponent bits, right? Number of exponent bits, right? And then number of fraction bits, right? In other words, for instance, I give 8 bits to represent exponent. I give, for instance, 11 bits to represent fraction. Then once this input is given, then your program should produce triples. Triples representing this minimal power, and this power, and then this power. So this is what I want to see, right? Because it is minus minimum power, and then minus this number, and then this number, right? So once we have these things, we can find a clear, exact boundary, right? 2 to the power of this boundary is the smallest number that we can represent, and the maximum number that we can represent is 2 minus 2 to the power of this number, and then this number. So this is what I want to see. So on problem 3, any number of bits can be plugged in here, right? Then you must find these 3 exponents. Because once we have these 3 exponents, we can determine the boundary of the number. In other words, under this assumption, we can say that the smallest number is 2 to the power of minus this number, and then smallest number is here, and the maximum number is 2 minus 2 to the power of this number, and then 2 to the power of this maximum number, right? So this is the minimal number, this is the maximum number that we can represent. And then once you do it, you can design the bits on your own. In other words, how many exponent bits might be necessary or optimal, and how many bits might be optimal to represent the fraction part. So I explained everything, and if you have questions, ask me. In other words, before going any further, I will run this pseudo function. Range of exponent bits, like what did we use? Exponent bits is in IEEE 754. The number of exponent bits is, I guess, 8. 8, right? And then fraction bits is 23, right? So assume that you plug this in, then your program will run and then produce this answer. The answer is I forgot the number. Do you remember this number? Minus 149, right? And then this power, right? And then this power is 23, right? And then this power is so you should write this answer, right? So these determine the complete range, right? And then if we really calculate this number, it's not exact, but now not exact, right? This is exact range, and this is approximation. Approximate range is from 10 to the power of minus 44.85 through, this is approximately 10 to the power of 38.53. So we know approximate range in decimal, but what I want you to do is not just to approximate. I want you to find the exact range representing powers. Not the actual numbers like this, but the powers I want. So this is what I want to see, and if you have any question about this, ask me. If you don't, then I will begin to cover the next two.
Question 1, do you want us to also handle the cases of not a number, infinity, minus infinity?
Oh, you don't have to. You just represent everything between this minimal power and the maximal power, and then you may add the sign. It's not very difficult, right? So please check whether you completely understand the problems or not. If you don't, then you may ask me. Then to check whether you completely understand these things or not, I will ask one more question. Assume that we have double precision, then we use 11 exponent bits and then 52 fraction bits, right? Then what is the result? If we do this, then what is the result? You should get the triple, right? So can you get this result? What is it? You have no idea?
What?
11 and 52.
get negative 1,074.
And then?
52.
And then?
1,023.
Great. Because I cannot memorize this thing. One, 023. So you should get this answer, right? So I want you to create this kind of program. And as you can see, middle one is very trivial, right? Middle one is easy. You can just copy. So you write a function having 2 input values and 3 output values, and middle number just is the copy of this second input. Yes?
Is 23 supposed to be negative?
I see. Yeah, you are right. Yeah.
Thing that he wrote for his sample, he put it as a negative.
So yeah, anything is okay, but yeah, I will be clear. So this way I can just make it, everything now has even negative, right? You can have negative. And then this is the smallest number, 2 to the power of, this is the smallest number, right? This is the smallest. Then now this is negative, and this is positive, right? Negative, positive. Let's be. But it doesn't matter. Once I read your result, then I can know whether you meant what negative one. So do you completely understand the situation? And theoretically, do you know why this is so? Or you need more examples? Great. So in my opinion, I explained all the necessary stuffs. And finally, before going to the going to the numerical techniques, I will let you know one more, let you know the technique that I showed you before. Assume that you have number written this way, right? Like a_n, and then point a -1, a -2, up to some number like a -k, right? Assume that you have this kind of representation with base b. Then, by definition, it is equal to an b to the power of n, right? And all the way up to a1 b to the power of 1, a0 b to the power of 0, and then a -1 b to the power of -1, all the way up to a -k b to the power of -k, right? This is the definition, right? The very first definition that I showed you. The very first definition that I showed you, right? This is the definition that I showed, right? Then, in programming these things, how can we determine these numbers? How can you determine these numbers? It's not very difficult to determine these numbers. So it's not very difficult to determine these numbers. How? First of all, this is what you do. Forget about the fraction part. We can handle the fraction part later, so forget about this fraction. Then, what you need to do is this one. Divide everything by b. Then, these will be all divided by b. These will be divided by b, right? Because you divide by b base, these will be divided by b, because we have at least power 1, right? So if you divide the given number, by b, then everything will be divided upstairs. And the only thing remaining will be what? a0, right? So if you divide by b, then the remainder is a0. Do you follow me or not? Then, because you divide this by b, you have the quotient. Quotient is a_n bn plus a1b1 divided by b, right? This is the quotient, right? Because you divide this by b, the quotient is this one. And then this b and b are cancelled out. So if you apply the same idea, if you divide this by b, right? If you divide this by b, then the remainder will be what? A1. In other words, finding A0, A1, A2, these things are not difficult. Just divide by the base, and the remainder is B, A0, A1, AI, right? So you go all the way up to 0, right? That's it. Then what about this thing? How can you find these things? Because you have b to the power of negative 1, you multiply by b, right? Fraction part. Fraction part, you multiply by b. So you multiply by b. And then any integer part, right? Any integer part become a negative something, right? A negative something, right? For instance, negative 1, right? And then you multiply b and then subtract that part, and subtract that part, subtract that part. So this is what you need to do when you program stuffs, right? So you divide and then get A0, A1, A2 all the way up to something, and then you multiply, and then you get fractions. And if you want to truncate, you stop at some place. If you want to do round off, then after determining the final value, check whether that value is close to the left hand side or right hand side. If it's close to the left hand side, you truncate. If it's close to the right hand side, then you increase the number, increase the previous number by 1. And then if carryover is necessary, to carry these steps. So I will show you one more. I will show you these things with examples. Cover the next step. Because you need to program this part anyway, right? For instance, assume that you are asked to, I will use this kind of number, right? Assume that you want to convert these things to bits, right? IEEE bits. Then, first of all, you should convert these things to binary numbers, right? You should convert these things to binary numbers, meaning you should find these things, A0, A1, A2, all the way up, and then point A minus 1, A minus 2, and so on, right? So you should find these things. Any questions? Then let's do it. We forget about the fraction part initially. We consider 13. Then 13 is here. Divide by base, right? Base here is 2, right? Divide by base, right? Or base is 2. Then the remainder is what? Remainder is what? If you divide this by 2, what is the remainder? 1. This one is A0. Do you follow me? A0 is determined. A0 is determined. Now the next step. The quotient of this, if you divide this by 2, the quotient is 6, right? So 6 divided by b. Then the remainder is what? 0. That is A1. So A1 is determined. If you divide by this 2, then the quotient is what? 3, right? Quotient is 3. If you divide 3 by the base, b, then the remainder is what? 1, right? This is A2. And quotient is what? 1, right? If you divide 3 by 2, the quotient is 1, remainder is 1. If you divide this by b, then the remainder is what? Remainder is 1, right? And then it is A3. And then if you divide this by 2, then quotient is 0, right? Because we have 0, you don't have to go any further. So we found these numbers. So 1, 0, 1, 1 is the number that you need to find. Right? So you should create this part. Now, let's do the same thing to determine the parts for A negative 1, A negative 10, and so on. So let's do it. Now fraction reverses these steps using, instead of dividing, we should multiply, right? So I will show you the fraction part. Number is 0.25, right? 0.125 and multiply by base, right? Multiply by base, in this case 2, right? Then, what is the result? The result is 250, right? And do you have an integer part or not? We don't have integer, so no integer, right? So integer part is 0. This is a negative 1. Now, we multiply this by base, right? Multiply this by base. Then 0.500. And do we have an integer part or not? No integer part, so it is a negative 2. And then multiply this by b, then it is 1000, right? And do you have an integer part or not? 1. Then this is a minus 3. And then subtract this integer part, then 0 happens. Then you don't have to go any further. So because of this reason, we found 0, 0, 1. In other words, 13.125 in decimal number is 1101.001 with binary representation. And later I will use a different example. Assume that it doesn't stop like this, then what should we do? That kind of thing will be shown very soon. But do you completely understand everything up to this point? Then let's continue. Then this kind of number, 1101.001 with base 2 should be represented somehow. If we design bits using fixed floating point system, then we can represent this thing directly as bits, right? Directly convert this to bits. But we don't use this kind of fixed floating point system. So we should write the standard form like this, 1.101001, right? We should use this kind of 1 to 3, right? So we should represent it this way. So initially convert the number to binary numbers, right? And then represent the binary numbers using standard representation. Afterwards, you convert this to bits, right? So sign is plus. That means first bit is 0. Off, right? And then exponent is 3, right? Exponent is 3. So if you use 8 bits to represent exponent, 3 is 1, 0, 0, 0. 0, 0, 0, 0 is 1, right? This is 1. Then 1 added, 1 more added, right? Then it is this one. So it is 1, 0. Or you can add bias to this number to create this kind of binary number, right? This number plus bias gives us this kind of binary number. You regard this as a binary number, right? This number plus bias gives us this. And finally, fraction bit is, after removing this number, right? After removing 1, it is 1, 0, 1, 0, 0, 1, and then fill these things with zeros, right? This is it. So your program should do these things, right? So the top part should determine this kind of a sub I, right? Top part should determine a sub I. And then after determining these things, you should convert these things by moving this floating point to some position, right? And usually you can determine this by using this index, right? This index is in fact exponent, right? Index giving us 0 is the exponent, right? Do you follow me or not? Index giving this 0, right? Index giving this 0 is the exponent, no matter what. So in your program, you follow that number, and that number is, sign is obvious, right? Sign is obvious. Then only thing remaining is fraction. Then you just read numbers after excluding this. So you read these numbers and cut. your program should do these things. Then finally, what about non-stopping, right? Infinite, right? Infinite sequence coming here, following here, right? What if infinite sequence after this floating point? That kind of thing will be mentioned, unless you have questions up to this point. Any questions up to this point? Then finally, assume that fraction is bad, like this. So I will not worry about anything before this floating point, so I will worry about the parts like this. So you may pick number, then I will convert it. So pick a number. Pick numbers.
0.2.
7.
0.2.
0.2. And then I want to use long number.
Well, 2 doesn't work out nicely.
Oh, I see. 2 might be good enough then.
Now we don't have to figuring out everything else.
I see. So this might be good enough, right? So assume that you have this thing, then how to convert it? So let's do it. So multiply this number by base, right? Multiply this number by base. Then it gives us 0.4, right? And then this gives us a -1 is equal to 0 because we don't have any other part here. Multiply this by b gives us 0.8, right? And then this gives us a -2 is 0, right? And the next thing is multiplying this by b gives us 1.6, right? 1.6 if we multiply b. Then a -3 is 1. Do you follow me? And then integer part is chopped, right? Chop this integer part, and then write the number after this floating point, right? So 1 is chopped, right? 1 is chopped. And then 0.6 is here. And then multiply this by b, right? Base. Then what is the result? 1.2, right? Do you follow me? Then, because of this a, -4 is what? 1, integer part, right? Integer part is negative. So let's check whether we found everything. So 0, 0, 1, and then 1. And then multiply, chop this thing, because we already recycled it here. Chop this thing, and then multiply this by b. Then 0.4, right? Then it is a -5, because there is no integer part. And then multiply this by b, then 0.8, and then a -6 is 0 because there is no integer part. And then multiply this by b, then it gives us 1.6, then it's a -7, right? Because of this one. So we can somehow find a pattern, and 0.2 in decimal number, 0.2 in decimal number is equal to, if we recycle the result, 0.001 and then 1 and then 0011 0011 0011 and so on, right? If you follow this pattern. But assume that you are allowed to use, so I will change the problem. Assume that you want to convert. So you now know this thing, right? It continues, right? Theoretically, this continues if we don't have any stopping point. Now we impose the stopping condition. Any questions up to this point? So assume that you are converting 1.2 in decimal representation into binary representation. But it doesn't stop, right? It doesn't stop. So it's approximately equal to. So 1.0011, 0011, and so, right? So this is the representation. So you may pick the number of bits that you want to design. In other words, you design how many bits to represent fraction part, like pick between 3 and 7. What number would you pick? You are allowed to use how many bits to represent fraction? How many bits do you want? 5 bits? So 5 bits for fraction, right? Fraction should use 5 bits. So your design has 5 bits. Then what should you do? Then you normalize it, right? You normalize it. And then do you think that you can represent it 0, 0, 1, 1, 0, right? So this is the fraction part. You chopped it. Assume that you are allowed to use 7 bits. You are allowed to use 7 bits. Then where should you chop? 0, 0, 1, 1, 0, 0, 1. And then if it is truncation, you don't care about the following terms, right? If it's a truncation, you don't care about the following terms. If it's a round off, then after finding this, right? After finding this, if it's a round off, then you should examine one more term, right? That will not be represented at all. Because we have only 7 bits, we cannot represent the next number. But at least we examine it, and if it is close to 1, then we move to the top number, right? So it is close to something, right? If it is 1, it should move to 1. If it's close to 0, then it should move. So what is the following number? This is the following number, right? And this is 1. This means we should add 1 in the last digit, right? So what happens if we do round off? Then it is 0, 0, 1, 1, 0, 0, 1. But 1 added here gives us 0, 1. So this is the round off result, right? So round off is harder to program. Truncation is easier. Unfortunate case is this kind of thing. Sometimes we may have this kind of number. Right? Assume that you have this kind of number, and then we are allowed to use 10 bits to represent a fraction, and round off is required. So this is a situation. Then we should chop at 10 bits. This is not necessary because of normalization, and we should use 10 bits, right? So 5 bits here, and then 5 more bits here. 5 more bits here. And then we should chop at this position, right? Chop at this position. And as you can see, the next number after chopping it is 1. That means we need round off, right? So after chopping it, we should add 1 because this portion, especially this part, is 1. So we should add it. Then adding gives us carryover all the way through. So eventually what we will have is this one. 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, right? This is the bit representation of the number after round off. So round off is harder to program. But most computers do round off. It checks these things, and then I showed you how to round off on exam program solution, right? Exam program solution, I showed you. You go from the bottom and then check whether it's 0 or not, right? So bottom, and then how do we do it? If it is 1, we convert it to 0, and then you can carry over and then do the same thing all the way up to some part having 0. And that when you see 0, we convert it to 1 and then stop. So in this sense, the number can be written this way, right? Assume that we have some number, some decimal number, and then some decimal number has this binary representation. Right, this binary representation. But if we are allowed to use just 10 bits, right? 10 bits, then 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, and then we stop, right? We should stop. Right? This is the bit representation of the fraction part. And then exponent part should be 1, right? Exponent should be 1, right? This is the exponent part. And then sign bit is 0, right? So sign bit, exponent bit, fraction bit. So in fact, initially when people created computer, they did these kind of things. And it is also handled by all hardwares. So please browse these things and ask questions. If you don't, then I will cover numerical techniques.
Can I ask one question?
Yes.
So when we're figuring this out, I mean, we have to figure out all the bits to the left and all the bits to the right of our decimal, and then we compile them and count down to whatever we have and whatever truncate the rest.
Right. That's right. That's the reason why it's inevitable to encounter error, because we have these many number of fraction bits, right? Like even in double precision, like 52 bits, right? So if somehow the part before the fraction is big, right? Like big, and then this part isn't very difficult, right? Assume that you have this kind of number. Then what happens is this one. First of all, we should convert this to binary numbers, right? Then it will be long, right? It will be very long. Binary number is long. But if it somehow already occupy 52 bits in the fraction part, even the part like this might not be correct. That's what happens if you multiply two big numbers in MATLAB. If you multiply two big numbers in MATLAB, somehow the number, even integer part, changes. Why? Because it uses this kind of number scheme. It can hold at most 52 bits with accuracy, right? Because of this reason, some number should be chopped, right? Somewhere it should be truncated or rounded off. So I will really show you the case. Right? I write this down, and then to check whether you can really keep it or not, I will add many ones, right? Take a look. As you can see, it chops at some point, right? How can you increase the precision? Do you know the command? Format long, right? And then let's do it. So where did it cut? It cut the number about this point, right? In other words, these are gone. These are gone. So when you use MATLAB or C or something, you should know this fact. If the number is too big, you cannot expect the precision about the positions like these, right? These kind of things are all lost. So precision doesn't just depend on, I will show you, the precision doesn't just depend on the depth. In other words, someone may ask you, oh, can MATLAB handle or can C handle these kind of things, right? And the answer is yes. Why? Because it doesn't have many numbers. In representation, it looks like this. It is 2 to the power of something with 1, right? But what is the difference between this thing and this thing? Then as you can see, oh, in this case, you can even handle the number with these many numbers after the decimal point, right? While it can handle this kind of number, why cannot this handle these kind of things? The major reason is this. We have a certain number of bits to represent the whole number, right? But in this case, the whole number starts at this point, right? In this case, the whole number starts at this point. So we should somehow allocate some position to represent these kind of things, right? Then 50 bits might be all used up even before it comes to this position. So you should clearly see the reason why sometimes we cannot get the accuracy of this kind of thing. So it is very limited. Yes?
Does MATLAB use 32 and 64?
I have I didn't design MATLAB, but usually if people did not add the part that you did in homework 1. In homework 1 you calculate then they just rely on C language double precision part, right? That means like 64-bit double precision is used, unless they specially added some algorithm part. So usually, I don't know how MATLAB is designed, because in Maple, there is no limitation. You cannot even imagine how large it can handle. I didn't see big limitation. So this is already over 100 digits. So how many digits can it handle? So I will add the variable. Then how many digits are there? Can you guess? So log about 386 digits. About 386 digits are written. Then a squared will be large, right? A squared will be large. It exactly handled it. It didn't lose any precision. So as I mentioned before, precision comes from the number of bits allowed for fraction part, right? These many can be kept. Outside this, there is no guarantee. So sometimes you can keep this kind of small number. Sometimes even this number cannot be kept correctly. Why? Because certain amount of number, right, or certain amount of number of bits are used, right? So certain bits are allocated. Other than these things, you should chop, right? You may chop at some point, right? Any more questions? Then numerical technique. And numerical technique is roughly about 20% of stuff covered in numerical analysis. We don't have enough time to cover everything covered in numerical analysis, so we select the most important things, like 20% of important things from numerical analysis. And last time I mentioned about root finding and integration. Do you have any questions about these things? And as I mentioned before, this integration is very, very important in handling PDE problems or even ODE problems. Assume that you are asked to solve this kind of differential equation with initial conditions or boundary conditions, then instead of directly solving differential equations, you solve weak form involving integral, right? Integral from alpha to beta, y second derivative minus y multiplied by, we'll define basis functions later, right? So we will handle this kind of things. Then for each base function, we have one equality, right? So from one equation, we derive many equations, right? We derive many equations. Then we solve system. Instead of solving differential equations, we solve a system, because once we create this kind of integral, we can simplify these things to create a system. So instead of solving a differential equation, we solve some system. And then how many? It depends on I, right? I is 0 up to n, stuff like that. We cover. Then the next thing is, so first thing was root finding. Second thing was integration. But before going any further, roughly, because we covered the integration, we can cover differentiation too. But compared to integration, differentiation is way tougher, right? Integration and differentiation, in theory, are similar, but practically, in numerical analysis, integration is way, way easier than differentiation. In theory, what is easier, differentiation or integration? Differentiation is easier, right? So in theory, in mathematical theory, differentiation is easier than integration. So differentiating this or integrating this, what is easier? Differentiating this is easier, right? And in numerical analysis, integration is in some sense easier or having better result than differentiation. Better result. Easier may be a little bit vague, but the result is better than differentiation. Why? Because of this reason. We accumulate thin pieces, and then eventually, compared to this big result, small difference, right? Small difference occurring here, right? And then small difference occurring here, and then small difference occurring here, right? Compare the size. The difference between the actual value and this one isn't big, right? Difference isn't big. Because of this, it is easier or better result, right? We have a better result. But differentiation has this problem. We should divide by small increment h, right? The small increment h. In fact, to really define differentiation, we should take a limit as h goes 0. Problem is this. In integration, as I mentioned before, the error is small compared to the total area. The total area is this large, and error is this much. In differentiation, as h becomes small, as you can see, there is limitation here, right? And then we have a certain number that we can allow. That means some number might be chopped in the first place. Because of this reason, the denominator is very unstable. So slight change in the denominator may result big difference in the bit representation. Then that kind of last part might significantly work in the result. That means the error may be bigger, right, than the error that you can see there. Compare the total result. Compare this total result, right? Compared to this total result, this error is insignificant, right? But here, this small error may blow up this value, right? So I will show you an example. So somehow we are using h, and then h is small, right? H is small. But assume that because of truncation, assume that we lost this number. Do you follow me? Compared to the result there, assume that we lost to this number. Because if you truncate, this h and 0.00014 are the same because of truncation, or even round off, right? So you see the difference, right? Actual number is 0.00014. Our h is 0.00010, right? This is our h. Then as you can see, if you do round off a truncation, this will be lost. Then take a look. Assume that y of x is x to the fourth, and then x, we consider the point 100. So assume that we consider this kind of x. Then what happens? Then y of 100 plus h minus y of 100 over h will be calculated, right? To calculate the derivative. Then what happens? (100 plus h to the power of 4 minus 100 to the power of 4 over h 0.0001. In fact, 1,4 is the correct result, right? 1,4 is the correct result. So you can use h equal to 0.00014 and then get the value, right? Get some value. And then you can use h equal to 0.0001 and then get the value. And then check the difference. Do you know what I mean? Actual value should have been this one. Should have been this one. And then we should get this result. But because of truncation, my program cannot store this kind of value. Right? My program chops this, and then eventually what it does is this calculation, right? Right? Because of truncation. Essentially, you don't even see the difference. What you see is just some number that you derive. Do you completely follow me or not? So actual value h is this one, and then you should have given this one, but somehow your program run with this kind of number. And so with Maple, let's calculate it. So I will write this portion and then do it. H is equal to 0.0001, and then later I will change it to 4, right? And then 100 plus h to the power of 4 minus 100 to the power of 4, and then divide by h. So let's call this value approximate, right? Approximate. So approximate value is this one. Now I will change h. And then 1,4 is used. And I will call this exact value, right? Exact value. It's very strange. Why did this happen? It's powerful. Do you see the reason, or it's very strange? It should be very different, and I don't. Strange. Is it coincidence or something happened? It should have been. There should have been a huge difference, but somehow it is the same. So I don't know the reason. The function too simple, or
You use the same letter H.
oh, I see. This is still large. This number is still large. So let's change this number to something. Somehow, I now know the reason. This is self-truncated. This is self-truncated. Do you know what I mean? So to do it, I will do the exact calculation. So because of the error, I couldn't show you the error. I will let you know what I meant. Just a moment, I'm struggling now. I might use different number. I used a different number. 1 point. What should I do? 1/4. 1/4. Yeah, what I meant is 1/4. Oh, yeah, one more zero. Sorry. This way I can. So do you see the difference? Because in the previous result, Maple itself also used numerical method, meaning chopping some point. Do you know what I mean? In this case, by doing exact calculation, now you see the difference. So this difference is created. So theoretically, I did the same thing. But in the first step, I used point something, and then when Maple says point something, it automatically used numerical method instead of exact method. So I forced the Maple to represent the number exactly. In other words, instead of using 0.0001, I used 10 over 100,000, right? And then I used, instead of using 0.00014, I used 14 over 100,000. All sorts of trouble. So do you clearly see the similarity and the difference? Yes. The only avoiding decimal representation, floating point, once this is floating point representation, it automatically uses numerical method. It chunks itself. So that's the reason why I got the same result, very strangely, in the first. But as you can see, this is what I meant here, right? 0.0001 is written this way. 0.00014 is written this way. So you see the implementation of these things in exact form. Then we can calculate these things exactly. Right? Calculate the same thing exactly. Then end result, difference is this much or this much. So you want the accuracy of like 4 digits, right? Accuracy of 4 digits after decimal point. And you expected it. But because of this involvement, right? Because of this truncation part, this change creates this kind of huge difference. 2.4 is huge compared to this kind of accuracy. So that's what I meant. And please browse these things and ask questions. I was so very surprised when I first saw the exact result. So even Maple couldn't handle that kind of difference, right? Even Maple couldn't handle this kind of difference once it goes into numerical mode, right? So as you can see, the difference between the two, so let's say A and B, then B, right? A minus B difference is approximately 2.4. Huge difference, right? So it's impossible to avoid this kind of error in numerical analysis, especially when the derivative is involved. There is no way of representing derivatives correctly. Why? It is lose-lose situation. Why is the lose-lose situation? Assume that we want to get correct derivative. Then to get the correct derivative, we need the limit with very, very small h, right? So the smaller, the better. If we drop this thing, then automatically this is incorrect, right? If we drop this limit, this is incorrect. But if this is too large, then as you can see, y prime, and then this itself has certain amount of difference, right? Certain amount is difference already. Do you know what I mean? If h is very small, it's close. But if h should be greater than something, then already the difference exists inside this representation. So it's a lose-lose situation. If we increase this thing, then this increases, right? If we decrease this thing, then this kind of phenomenon happens. Because of this reason, differentiation is the toughest one in numerical analysis. And it also affects our method in differential equation solving. Because when we use finite difference method, we are forced to use this kind of representation, right? We are forced to use this kind of representation, then already, because of this representation, we have error. Yes?
If you're using a 64-bit or like a double precision bit structure, doesn't the number go small enough anyway that the error is very small?
That is our hope, but let's check what kind of thing might be the example. So let's make this a little bit, let's add about a few more zeros, right? Of course, in this case, it won't be very bad. So let's run it, and let's check how kind of error occurs. So it's small, but still exists, error exists, right? Still exists. because error propagates, right? Or somehow error affects some other results too. So in any case, I don't think double precision can handle this kind of accuracy. So you already studied about double precision number limitation, right? So a certain number couldn't be handled. So interesting question is this one. If you use double precision, the smallest number that we can represent, right, with double precision, the smallest number that you can represent is 2 to the power of something, right? I said minimum, right? And then, do you remember this number? 2 to the power of what? Right, this kind of number, right? So when you use double precision, we may keep some values like this, but when these are multiplied with big numbers, then we significantly reduce the accuracy, because we should use this to represent fractions. So it is not always this refined. So I will write the situation. So to do it, let's consider the number with 3 bits of exponent, and then 2 bits of fraction. Then write all the numbers. Then you will see how many numbers we can cover. Even though superficially it says, oh, very small number can be covered, you will see big holes. For instance, the smallest number that we can represent, the biggest number that we can represent, and other numbers in between, right? Other numbers in between. Then as you can see, there are some gaps like these. Of course, initially it is refined, right? Initially it is refined, and somewhere you have gaps. So you write all the numbers that you can represent using these things, and then locate and then see the gaps. So let's do it. Exponent bit, fraction bit, then this is the exponent bit, and then fraction bits like this. Then the smallest power is, bias is what? Bias is 2 to the power of 3 minus 1 minus 1, right? And then 3. Bias is 3. Do you follow me? So I will show you the representation. 110 is the maximum power. 101, 100, and then 011, and then 010, and then 001, and then 000. There are these range. The 111 is used for not a number or infinity, and then this is the 0 exponent, 1, 2, 3. This is -1, -2, -3. Right? So let's consider the normalized case. Then 2 to the power of -2, right? I said -3, this is not the case, right? This is denormalized, so -2 is the smallest power that we can represent. And then 0 point, there are 2 bits that we can use, 0, 1. This is the smallest number that we can use. Do you follow me? Then this number is equal to 2 to the power of -2, and then 1/4. So it is 1/16. And the next number has this one, so 2/16, and then 3/16. So I wrote 3 numbers that you can represent using these bits, right? 1, and then 2, and then 3. So we can write these numbers, right? Using 2 bits, right? Using 2 bits. Do you follow me? Using these 2 bits, of course, other than 0. This is 1, and the 10 is 2, right? 2/4. And then 1 is 3/4. So we can write these 3 numbers using the normalized bits. And the next number that we can represent is using 001 power. 1 point is assumed, right? Normalized bit, and then actual bits, right? These are actual bits. 0, 1, right? These are actual bits. Then it is 1.25, right? This is 1.25. or more precisely, 1 plus 1 over 4, 5 4, right, 5 fourths. So 5 fourths with this power gives us 5 sixteenths, right? This is 5 sixteenths. And the next number is 6 sixteenths, right? And the next number is 7 sixteenths. Do you completely follow me? So 1, 1, 0, 1, 1, this is what this is with this power. Then let's go to the next case. With 2 to the power of negative, here we used this case and one case, right? Minus 1. And then the same thing, right? The same thing. Oh, I forgot 0. 4 over 4, right? So 4 over 16 is forgotten. Now, it is the same thing. 4 over 8, right? And then 5 over 8, and then 6 over 8, and then 7 over 8, right? Because it can be 0 up to 0, 0 up to 1, 1, right? 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and all the way up to this thing. Do you completely follow me or not? So these numbers are possible. So let's stop here and then check the number. So the numbers that we could represent is this one. 1 sixteenth, 2 sixteenths, 3 sixteenths. So here it is refined, very refined. 4 sixteenths, 5 sixteenths, 6 sixteenths. So here it is okay, right? Up to this point everything is okay. But now, as you can see, 4 eighths, 5 eighths, 6 eighths, and 7 eighths. And it will become bigger, and the hole will become bigger and bigger as we go up. Right? Do you see the hole here? Hole is already 1/8, right? And then when you increase the power to 0, hole will become bigger. So when you go up to a big number, then hole will be very large. This is the thing that you have. So let's stop here, and let's resume at 307. Yes, thank you very much. So with 0.01, it is 1/4, right? 0.01 is 0 times 1/2, and then 1 times 1 over 2 squared. So it is 0.25, right? Or 1 over 4. So 1 over 4 multiplied by strange, I might do the wrong calculation. Yeah, right. I was confused. So this is the thing, right? So in this case, it's 1 minus bias is used, right? 1 minus bias. This is negative 2 power, right? This power is, both of these powers represent negative 2. But because this is denormalized, we don't have 1 supporting 1, right? Negative 2 here, and then 1/4. So 2 to the power of negative 2, and then 1/4 gives us this. So do you completely follow this line? This may vary from 0, 1 up to 1, 1. 0, 1, 1, 0, 1, 1. Then these are written. Because it's normalized 0, 0 allowed. 0, 0 means, normalized 0, 0 means 1.00 in binary representation, right? So these allow 0 because 1 is here. So with these things, we have these numbers. And then each time, the only difference is this part does not change, right? This part cannot change. The only part that changes is the power, right? Instead of power -2, we have power -1. Instead of power -1, we have power 0. Instead of power 0, we have power 1. Instead of power 1, we have power 2. Instead of power 2, we have power 3. All the numbers that appears here are same, 4, 5, 6, 7, right? 4, 5, 6, 7 with the denominator 4. So if I write the number that we can represent using this design, is this. Then as you can see here, it is misleading, right? It looks very small, right? Error looks very small. But here, as you can see, assume that you have some number in between, like 13 or 13.1. Then already in this number system, the error is huge. 0.9 is the error. So you cannot say, oh, error is small enough to ignore. No. Here it is small enough. But here it is not small enough. So this is what I meant, right? Do you clearly see the number system implemented in computer? So assume that you are handling some number around some big number like 14. Then the accuracy cannot be this nice all the time. In other words, it cannot be, I forgot the number, but roughly this kind. It cannot be this nice all the time. Right? It cannot be this nice all the time. Some error will propagate. So with this in mind, let's continue. So as I mentioned, in numerical method, compared to this, when we handle integration, compare this to this whole area, right? Compared to this whole area, the error that we encounter might be very minimal, right? If you accumulate all these errors in one box, then the error looks like this, right? Error looks like this, right? So error is not big enough compared to this big result, right? Compared to the big result, this ratio is very, very insignificant. But when you do differentiation, then as I showed you, when slightest error happens here, the total result may have big error. That's the key. Because of this reason, differentiation is the toughest part in numerical method, and we don't learn just one method because of this reason. In other words, some method works fine here, that does not work fine there. So we should use several. And this is the reason why finite difference method cannot be used for some problems, and the better method to handle the problem is finite element method. Sometimes it's okay, but sometimes it's not okay. So roughly, how we implement differentiation? We implement the differentiation this way. We make a grid covering the domain, right? Right? We cover the domain, and then we assign position representation. Like, for instance, we call this, I will use one-dimensional one to make it simple. Say x1, and then x2, right? And then x3, and then x4, and so on, right? And then we assign y values, right? Here y1, y2, and so on, right? y3, right? And then we calculate the difference, right? Such as y3 over y2, x3 over x2, right? And then we call this the derivative of this at x2. stuff like this. We define this way. It's not exactly equal, but we define this kind of way. So this is the way we use a numerical method. But as I mentioned before, this result or this kind of scheme is far from exact. Right? Very, very rough. So sometimes people intentionally increase the denominator to reduce the possibility of error. Right? The percentage of error may change. If we use small h, then small error here may be big. But if we increase the denominator, then the small error may not work as bad as the previous case. So this is what I meant. If the denominator is small, then small error here, right? Small error between this one and exact value, right? This is the one that computer uses, and this is the actual value, right? This is the actual value, and this portion is error. This portion of error may propagate. Here, if we somehow can enlarge the denominator, right, this part enlarged, then the same amount of error that occurs is proportionally smaller than this one. But unfortunately, if we enlarge this one, the part here hurts. The part here hurts. It's not close to the derivative. To be close to the derivative, this should be very, very close. So it's lose-lose situation. If we make it small, then this hurts. If we make it large, then this hurts. So this is the reason why differentiation is so tough, and there is no universal method to handle differential equations. In any case, I explained the whole necessary idea, and if you don't have a question, I will go to the system part or matrix part. It is impossible to avoid matrix in numerical method because many equations or many systems or description became a system, right? Equations, for instance, differential equation, one equation, right, becomes a system of many equations, as I mentioned, right? And then something describing the basis may become system and so on. So it is impossible to avoid system, and then system, especially linear system, can be represented by matrices, right? Then it is important to know the closeness, whether A1 is close enough to A2. In other words, we want to know whether we have reached the similar result or not. Then we want to define the norm of matrix. Norm of matrix A, right? Norm of matrix A. And because it's not numerical analysis course, I don't even give you the exact definition. If you want to see the exact definition, look at the summary, then you can find the exact definition. In other words, we can find the norm of a matrix. In other words, we can check whether two matrices are close or not by checking the norm, right? There are several different norms, and then check whether this is small enough or not. So norm is used to determine the closeness. Then the next thing is system. Among many systems, linear system appears frequently. So we will handle linear systems from this point on, and I will be very, very slow from this point on. Linear system consists of unknowns, right? Unknowns such as x1, x2, and so on, right? Unknowns, so xn. These are unknowns. And then coefficients. coefficients. And then system means many equations, right? Many equations. Then how can we find x1 through xn is very, very important. Take a look. In the future, you will see collocation method and finite element method, meaning you will define basis function for such as phi1, phi2, phi3 up to phi200, right? You will define this kind of basis function. Then the solution is a linear combination of this basis function, right? So solution looks like this: C1 phi1, C2 phi2 up to C200 phi200. These can be generated by some pattern, right? These are all uniformly defined, and the only thing that you need to determine is C1 through C200. Then the unknowns are C1, C2 up to C200, right? Unknowns are C1. And how can we get these kind of functions? We get these kind of functions by from the differential equation by integration. So assume that you are solving this kind of PDE problem. Assume that you are solving this kind of PDE problem. Then it's one equation, right? As a differential equation, it's one equation. But now you want to solve a weak form, right? You want to solve a weak, this is still strong form, but you want to solve a weak form. So you integrate, right? You integrate over some region, right? Some region with basis function like this multiplied. So you solve weak form. Then for each phi, we have one equality. So how many equalities will you have under this assumption? How many equalities will you have? We'll have 200 equalities, right? That means we have like something like this: C1, C2, C200 equals something from this one case, and then next case, next case, next case, and so on. So eventually we have 200 equalities. Then we should solve these things for C1 up to C200. Then, after finding these numbers, we can attach these numbers to find the solution to the differential equation. This is finite element method. So please browse the idea and ask questions. So solving system is essential in solving PDE problems, because PDE is generated by this weak form of 200 equations instead of just one equation. Then I will let you know the method. First method is trivial one. Assume that you have x1 plus x2 equals 2, x1 plus 2x2 equals 3. Then trivial method is this one. We remove this kind of thing by elimination. We remove this term by subtraction, right? By subtraction, we remove this one. So we subtract this line from, so row 1 from row 2. So row 2 minus row 1 will be written here. Row 2 minus row 1 result will be written here. Row 2 minus row 1 gives us 0, x1. And then 2 times this one, 1, x2. And then 3 minus 1. And then you determine x2. And then after determining x2, So from this you determine x2. You plug this in, right? This is 1. And then you determine x1. So this is the method, right? And this method is called Gaussian elimination method when you systematically handle a general system, n by n system, right? N by n system. So you can do the similar thing over and over again. And essentially what you do is this one. This step is called forward elimination. Right? You eliminate the number below, the coefficient below, right? You eliminate the coefficient below this, right? So below this, everything is eliminated. No matter how many equations are there, we can eliminate all these numbers by using this kind of idea. Do you follow me or not? And then you eliminate the numbers below similar way all the way through to create a upper diagonal matrix, right? So we created this thing. Then the remaining thing is this x1 plus x2 plus x3 plus x4 and so on equals something, right? Like 5, right? And then x2 plus x3 with some number, right? And so on is equal to 4 and so on, right? So you create this kind of system. If you don't think it's possible, then ask me. Or if you think it's too difficult, then ask me. Then I will show you why it is so. After doing this, by reading this, you can get the value. For instance, xn is found. x5 is 1, right? After x5 is found, like this case, after x5 is found, you plug this in here, right? To get x1, right? Because this value is known, you can determine this. So we use this value to determine this value, and then you use these two values to determine this value and so on. You go all the way back. It's called back substitution. So you back substitute to determine x5, x4, x3, x2, x1. You eventually determine everything. So this is Gaussian elimination method. And when you do these things, we generate the matrix like this, called upper triangular matrix. And then individual number that we multiply, like we multiply this row by 1, right? This row by 1 is collected here. 1 multiplied here, right? This number 1 is multiplied here. And then assume that you have 2x1 plus something. Then R3 minus row 1 times this number 2, right? 2 should be multiplied here, and then we can collect 2 here. Right? So we can collect these numbers in lower triangular matrix. So 1, 2, and so on can be collected. And then similarly, we can collect the number that is necessary to eliminate the coefficient can be collected here, and then it generate lower triangular matrix. Yes?
I got lost between going from the upper diagonal to the lower diagonal. Why are we doing that if we have already solved for those unknowns up there?
Oh, it is also completely solved. I'm covering the second method.
Second method?
Right. This can cover. So Gaussian elimination is essentially done here. And now, while we were doing this forward elimination, we created these kind of numbers to eliminate the coefficient below, right? So to eliminate the coefficient below like this, we multiplied 1. To eliminate coefficient like this, we multiply 2. So these kind of number can be collected here to create matrix. Then what happens is this one. Mathematically, we can write the matrix A by this lower triangular and upper triangular, assuming that this matrix consists of 1 in the main diagonal, and then these things that we recycled here, right? 1 in the main diagonal, and So L is given this way, and then these things are recycled here, then it generates L and U, and then L and U multiplied together is A. So this is the decomposition. Then the advantage of this is obvious. Assume that we need to solve a system like this, A, X is equal to B. Then instead of using A, we can use L and U. L, U, X equals B, right? Instead of solving AX is equal to B, A is now LU, and this one can be solved. And then I will go upstairs. LUX equals B need to be solved. So I will first call this Y, right? Then LY equals B should be solved. But because it's upper triangular, this is lower triangular, like this, 1, 1, 1, 1, and then 1, and then 2, and so, right? These things come here, right? And then all the way up is 0. And then Y1, Y2 is equal to B. We can read the solution directly. 1 times y1, and then 0 times y2, 0 times y3, 0 times y4, all the way through equals b1. Because of this reason, y1 equals b1. Do you follow me? Then, because y1 is found, y1 is a number, right? y1 is a number, then number times 1 is a number, right? Number plus this times y2, right? So number times this times y2, so 1 times y2, plus all the way through is 0, 0, 0, right? Equals b2, and then you can solve this for y2. y2 is equal to b2 minus b1, assuming that this is 1, right? So we can do these kind of things to determine y1 through yn. It's all elementary level linear algebra. Then we follow these things called forward substitution, right? Forward substitution, we can determine y1, and then by using y1 value here, right? This is y1 value. We can determine y2, and then by using y1 and y2 value, we can determine y3 all the way down, right? So y1 up to yn are found. Then, as you can see, because y is found, we can solve this system, right? Y is found, right? Y is found, we can solve this system. Y is found, right? We know the values of y. And we can solve this upper triangular system. How do we solve this upper triangular system? By back substitution, we determine xn by using this, and then back substitution determines everything. So once we have LU decomposition, we don't really solve the system. We do forward substitution and then back substitution to determine x1 through xn, right? Or just vector x. So with LU decomposition, AX equal to B solving becomes, solving this means solving LU X equals B means solving UX equals Y, and then L and this means Ly equals B, right? So that's just solving with this assumption, with this substitution. Solving this means solving Ly is equal to this. Solving Ly equal to this gives us Y. Then after this we solve Ux is equal to B. Ux equals Y. So take a look. There is a clear difference. It is not solving. Once you have decomposition, it is not solving. With this decomposition, solving this means solving Ly equals y, but solving Ly equals b is not really solving. It is doing forward substitution. Right? So with LU decomposition, solving is not really solving. It is forward substitution. And then back substitution. So this is the summary of LU decomposition with Gaussian elimination scheme. So with Gaussian elimination, we determine two matrices U and L, right? U and L. And then we do forward substitution to solve this system. And then after solving this system, we know Y. And then with Y, we use this upper triangular system. How do we do it? We do the forward substitution and the back substitution. So two substitutions will solve the problem. And if you have questions, you may ask me now or later. I do not ask any questions using these things because we won't use these things in this course. Knowing this might be helpful, but we won't use this directly in the course. Then the next method is the one that we will use. How do we solve the system more efficiently? This method is not efficient enough when we have a huge system. With small system, this is okay, but with a huge system, doing these things is difficult. And a lot of errors may happen, so we use iteration, and the idea is this one. So I will show you the idea. Assume that you have this kind of equation. Assume that you have this kind of system. Then of course it's possible to use LU decomposition or Gaussian elimination method. It's possible. But what we want to use is this kind of method. Oh, what about writing this differently? The same system written differently. How? We move this to the right hand side and divide by 5. Then x1 equals 1/5 7 minus 2x2, and x2 equals 1/3 7 minus 1/4, sorry, 1/4 So we create this kind of system. Do you follow me? x1 equals, if we move this and divide by 5, you get this one, right? And then x2 is equal to, you divide by this. Do you follow me? So this is the method that we will use. Then what is the difference? In this case, we should do the matrix handling. Matrix handling requires a lot of entries in the matrix, right? It doesn't just go through 1 through n. It goes through 1, 1, 1, 2, 1, 3, 1, n, and then 2, 1, 2, 2, and so, right? It goes through all the entries. But here, it goes through 1, 2, 3, and so on with just minor substitution. In other words, this relation determines x1. And then this relation determines x2. So, assume that we pick x1 and x2 this kind of way. Assume that we say x1, x2 is equal to, initially, like 1/2 and 1/3. So assume that we chose this kind of x1, x2. Then with this iteration, what happens? 1/2 goes in here, right? 1/2 goes in here. Then what happens? 1/3 goes in here. And what happens? 1/5, 7 minus 2 times 1/3. And here, 1/4, 7 minus 3 times 1/2. So do you completely follow me? This is the key idea of iteration method. So 1/2 goes in here, 1/3 goes in here, right? So 1/3 is written here, 1/2 is written here.
Why did you pick 1/2?
Just randomly chose. I randomly chose. Any questions up to this point? And then calculate these things. Of course, hand calculation is tough, but you are using a computer. So to the computer, this is nothing, right? This is nothing. So computer calculate these values. So from x1 and x2, we determine new x1 and x2, right? So x1, x2 become new x1 and x2. And from this these are some values, right? We plug this in here, and then we plug this in here to calculate new x1, x2. So this is the iteration method. We determine new xy, new x1, x2, new x1, x, new x1, x. We continue these things. So this is the method that we will use. And this system solving is extremely important. So we should convert the equation to this kind of pattern. Okay? And then determine it. So this method is called Gauss-Jacobi method if we simultaneously change the number. In other words, assume that x1, x2 are, I will intentionally choose different x1 and x2. So assume that x1, x2 are one half, one. So I intentionally chose different numbers because someone asked about the initial choice. I intentionally chose different. Then with this one, what is the next number? 1/2 is used here, then 6/5, right? 1/3 is used here, then 6/4. And with these things, we can calculate more other values, right? So we can continue these things. And if you don't think this is easy, ask me. Then I will show you more steps. Because you are not doing these things, I don't want to go any further because the computer program or your algorithm will do these things, iteration. So you keep determining new x1, x2, new x1, x2, new x1, x2, and goes on and on.
How do you know when to stop?
Great. So I will show you this example. So x1 equals 1 over 5 multiplied by 7 minus 2 times x2 times x2. x2 equals 1. It's not good. This is not good. It should be a function, right? If it's not a function, then is it okay? Yeah, let's try it anyway. 1 over 5, 4 times 7 minus 3 times x1, right? So I just rewrote the things that I wrote down in the whiteboard, right? So on the whiteboard, and let's do it. So let's do it. x1 is equal to 1/3, right? And then x2 is equal to 1/2, right? And then I used this thing. Then x1 and x2 can be found, right? And then I use this thing. New x1, x2 can be found, right? New x1, x2 can be found. So in essence, programming this is extremely easy, right? Just 4 lines will be a program with while loop, like 2 more lines will be a program, right? As you can see, we will go on and on and on to determine it. But as you can see, may produce exact value, so I will make it numerical value, right? Make them numerical values. So next number plugged in, next number plugged in, next number plugged in, and so on, right? So you should program this way, right? You should not ask me to return 100 times. So essentially, your program should do these things, right? Do you completely follow me or not? So take a look. Initially, I wrote this line somehow here, but in some sense, these 2 lines should be written upstairs, right? Right. So you should run this way. x1 is 1/3, right? x1 is 1/3. x2 is 1/2. That is a starting point. And then these iterates, right? So x1, x2, x1, x2, x1, x2, x1, x2, and so on, right? So I don't like to do these things, so I will use loop, right? So for I from 1 to 5 to, and then, right? Then as you can see, computer will do these things many, many times, right? So 10 times total, and then 15 times total, right? As you can see, after some point, the number does not change, right? The number does not change. So you asked about the stopping point, and what is the nice idea? There are 2 ways of stopping. One way is hardwired stopping point. For instance, take a look. Initially you start with these things, right? Initially you start with, and then you determine this kind of number. For instance, I will stop after doing 23 times, right? After iterating 23 times, I will stop. So then hardwired stopping is possible. This is hardwired stopping. If you don't like this kind of hardwired stopping point, then what you can do is this one. Use norm, right? I mentioned about the norm of matrices, right? Vectors are matrices also. So you can check whether this is smaller than your epsilon. So you pick your epsilon, right? You pick your epsilon, and then these 2 numbers, 2 vectors are close enough, and you can stop. So there are two ways. One way is hardwired stop. After running 23 times, no matter what, it stops. Or you add this kind of condition in the loop, right? And then you break if this condition is satisfied. So I completely showed you the method called iteration method. Then let's change the problem. I want you to make a problem, and I will solve the problem. So you make a problem. So let's solve a system of 3 unknowns, right? 3 unknowns. So you may pick your number. What number do you want? Please let me know the number.
1.001.
I don't like to use fractions. I want to use the integers. 2. 16. And then one number? 3. And then what number do you want? Negative 2x1. And then? 5x2. And then? Minus 4. Equals what? Equals what? And then what number do you want? I will pick my own number then. I feel threatened. So this is it, right? So I created a problem, and usually dividing by a big number is good, right? Dividing by a big number is good. So I will even though it's possible, I will.
So we can basically start this by picking any initial values for the unknowns and iterate it until the differences become 0.
Almost there. As far as some conditions are satisfied, like some dominant condition, something like that is, but that is a little bit abstract. But as far as conditions are okay, then we can use this.
I don't see off the top of my head why the differences.
Thank you. So this is xn and xn plus 1. These are not just numbers. So I want to solve this system, and I do not know whether it will behave nicely or not because it doesn't satisfy some condition. Then we don't know what may happen. So I try very hard to somehow make it nice, but my best try is this one. I will use this thing to determine x1. So I'm just trying it. So x1 equals 5 minus x2 minus x3, and then divide by 7. Do you follow me? Anybody can find the nicest thing. In other words, I want to use biggest denominator possible, and then I want to use this denominator, x2, right? So x2 equals something over 16. I want to use big denominator, right? 3 minus 2x1 minus 9x3. And then finally, you don't have any option. So x3 equals negative 7 minus negative 2x1 minus 5x2 divided by negative 4. So I wrote down these three things, right? Or you can make it better. So if you completely follow me, then I will continue. If you have difficulties, you can let me know. I will try to solve this system. Then, while you are copying it, I will program it. My program is very primitive program, but it will run. x1 is equal to 1/2. x2 is equal to 1/2. x3 is equal to 1/2. And then x1 is equal to, I will make a loop for I from 1 to 1, right? x1 equals 5 minus x2 minus x3 over 7. x2 equals 3 minus 2 times x1 minus 9 times x3 over 16. x3 equals 7 minus 2 times x1 plus 5 times x2 over 4. Did I make any mistake or not? I multiplied -4 everywhere. -4, -4, -4, -4 multiplied everywhere. So this is the first iteration, right? And then let's iterate more times. Because I don't like to look at exact values, I will calculate the numerical values, right?
You just ended the loop?
Yes, right. It is like Unix. Unix has if, then the end of if is called fi. Or case, then we reverse it in Unix shell programming. So are we converging? Do you see any kind of convergence? Similarity? Do you see similarity?
Yeah.
So I will run it wild, right? I will run it wild. It's not me who did this. So as you can see, x1, x2, x3, right? So very close, right? With some tolerance or error, allowance of error, we can accept it, right? So we can find this.
It's like it's the last digit is flipping.
Yeah. So because numerical value has limitation, they are they are like flipping this way and that way. Sometimes it goes this way, sometimes it goes that way, and then back and forth. So we cannot make it any better in numerical limitation that I showed you, right? In any case, this is the situation. So this is called iteration method. So if you have any questions about the idea, ask me. If you don't, then I will continue. But as you can see, I technically used big denominators here, right? The bigger the denominator, the better, right? So the bigger, the better here.
The initial values that you choose, is there no criteria to start?
As I mentioned before, we should have nice conditions, nice initial condition, nice denominator, this kind of stuff, like diagonally dominant stuff or something like that. But those are not the major thing in this course. In this course, we want to know this kind of technique, just iterating and iterating to determine the right. Then now, this is what I implemented was not Gauss-Jacobi. What I implemented was Gauss-Seidel, and they are almost the same, so you don't have to see the difference between the two now. Well, we can add one more thing. This acceleration level or speed is not good enough, so I will show you the reason. So as you can see, the acceleration that I showed you is not good enough. For instance, right after like 23 iterations, I want to get the result. So let's start off, right? This is the starting point, right? We initially started with this x1, x2, x3. And then we iterate these things 23 times. Then are we close enough or not? It's still rough, right? It's still rough. Do you see that it's still rough? So that means to get better result, we should accelerate, we should iterate more and more and more. So to accelerate to these kind of things, mathematicians twisted this kind of thing a little bit. What they did was this one. Theoretically, you can write an equation this way. We have this kind of equation, and I will add this kind of condition. So initially, I will keep the initial situation. Initially, this is the equality that we want to handle, right? Initially, this is the equation that we want to handle. Do you follow me? So essentially the same equation. The only thing that I did was adding and subtracting k, right? Adding and subtracting k. So essentially, x equals b did not change at all. But now, I will write it this way. So do you follow me or not? I just did some algebra, right? So initially x equals b did not change at all. I just added k and subtracted k. And then now I split 1 minus k to the right hand side, that became k minus 1. 1 minus k became k plus 1, k minus 1 on the right hand side. Now I divide both sides by k. Then what happens? So essentially the same equality, but what I did was adding k and subtracting k. Now let's call k over 1 w. Then x equals wb plus 1 minus w x can be used. So we call this method relaxation. And if usually w is between 1 and 2, if w is 1, then we call this Gauss-Seidel method. If w is less than, between 0 and 2. Between 0 and 2. 0 and 1 is called under relaxation. If w is between 1 and 2, is called over relaxation. So this is it. So in this course, what we will use is this over relaxation. So successive over relaxation will be used in the course. Sometimes people call this just the relaxation method, right? Relaxation method. Sometimes people call this SOR method.
Can we stop for a second? Tell me why we went through all of it. Why did we do that? We first start out with a vector x, which is basically an unknown, and we set it equal to a matrix of values that is known. Okay. And so our problem is to solve the x vector. Is that correct?
Yes, solve for x vectors, right. Yeah, so as far as solving is concerned, we can solve it. The reason is this. We don't want to iterate too many times. So we want to reduce the amount of iteration times. So to do it, people tried many things. And one of the things...
When we first started out, we had a vector x equal to a matrix of values b.
Right.
That matrix b was filled with known values.
Right.
I guess I'm not understanding what we're trying to do.
Forget about the initial starting point. Just focus on equation like this. We want to solve this equation, right? Assume that you have solved this equation. It's already solved, right?
Right.
We want to solve this equation, but differently. So to solve this equation, already x is equal to b, we know that, right? So we approach differently. So to solve this equation, I added and subtracted k and then did this kind of calculation to create this kind of equality. This equation is the same as this equation, exactly the same. So what I did was just rewriting x equals b. So forget about other situation at this point. Just look at this part. Do you completely understand everything up to this point?
I certainly I followed that, but
and I will connect this thing and the system later. So this is what I did. And then if this w is greater than 1, it's called over relaxation. If w is less than 1, it's called under relaxation. If it's exactly 1, it's Gauss-Seidel-Mess. So I just explained this relation, right? Essentially this and this are the same mathematically, right? But if we use some number w greater than 1, it's called over relaxation. That's all I wanted to mention. Now let's return back to system. We want to solve a system, right? We want to solve a system like this. Solving a system means doing iteration like this, right? Do you completely follow everything up to this point? But here at this point, it is like this. We regard this as x, right? We regard this as x and regard this as b. Then, if we apply those stuffs, then it's over relaxation and under relaxation. So all I need to do is doing what? Attaching these stuffs. Instead of just saying this, instead of saying just this, we attach these things, right? So instead of just saying this, I attach these things, then it's over relaxation. So I will make this over relaxation. So I will override the previous thing with red color. So what I do is this one. I attach w here, right? Attach w, and then 1 minus w times x1 here, right? Do you follow me? And then I attach w here, and then I attach 1 minus w x2. And then I attach w here, and then add 1 minus w x2. So this is what I do. So over relaxation is just simple equality rewritten. Then let's see the effect. Let's see the effect. But before seeing the effect, if you have any questions up to this point, ask me. Then I will attach these red parts. I will attach these red parts in my program. So in my program, I attach W, so I will define W, right? So I will define W, and then if it is greater than 1, it's called over relaxation. So I will pick such number as this one, right? 1.4 is chosen. It shouldn't be 1.4, but I just chose this number, and then W times this value, right? And then plus 1 minus W times x1, right? Everything evaluated, right? And then W times this one plus 1 minus W times x2.
What made you pick 1.4?
I randomly chose any number between 1 and 2. So you may pick different numbers. So W times this one, and then 1 minus W times x3. So look at the similarity and the difference. Essentially, these are the same, right? Essentially, these are the same. As you can see here, x is equal to b. X is equal to b is the same as this one, right? If you doubt it, you solve this for x. If you move this, then you will get what? Wx, right? And then W can be cancelled out, you can get. So essentially the same thing. But when you do these things, we call this relaxation, right? We relax this thing a little bit. So let's run it. Let's check what happens. So it's this situation, right? And then with relaxation, yes?
You have a typo there. Right there, yeah. Should be W.
Thank you. So let's run it. It becomes worse. What is wrong? Do you find anything wrong here? 1 minus Wx. So let's use different relaxation. It is not good enough. So I guess in the first place, what he had was a bad system. As I mentioned before, this is bad because here 5 is a 4. So we have some bad case. That's the reason when it's nice, it works, right? When it's nice. Because this system isn't desirable system, we cannot guarantee any convergence. But what you do is this thing. With this over relaxation with nice condition, right? Usually.
Nice condition meaning you have a nice system that
will have a solution. Solution, and then with diagonally dependent system. Unfortunately, in the first place, you chose some numbers that didn't have that kind of things. I tried very hard, but I failed. But in any case, this is called successive over relaxation or SOR method. Unfortunately, our example wasn't good enough, but when it's diagonally dominant, then it works.
When we did it before we did the relaxation, we were getting solution.
Right.
So the relaxation method
that's right. It isn't necessarily best. Why? Because we are in some sense jumping. we are jumping. Jumping could be good when it reaches the point, but jumping could be bad when it falls cliff.
Wouldn't the optimal case be when W equals 1? I mean, I don't see the advantage of this over the Gauss-Seidel method. That's going to converge, right? This may or may not converge.
The same thing happens. Even Gauss-Seidel may not converge when the system is not good. When the condition, the diagonally dependent thing is given, then it converges. Under that condition, we can use this.
And all three would converge. All
Right.
converge.
But the speed is different then. But here we have very unstable situation. Somehow Gauss-Seidel could converge, but success. So that's the reason I said nice, right? So with nice system, we can have converge.
Go back and plug in W equals 1 and see what that does.
Then it's exactly the same. The same. So, but now, because you want, I will do it anyway.
You could change the system to a nice system and show.
Yeah. So let's go back to a nice. Right? So this is what happened before, right? So with 0, it is pretty nice, right? But with jump, it isn't very nice. So it is about the unstable area, but later I will change the number. But let's try what may work. At least about this much. Does this help? Not very much, right? So let's change the system. Assume that we have a different problem in the first place. So let's change this to a nice system. So here it should be dominant. This should be dominant. So I will remove this number. Is it okay? Is it okay to remove this number?
For a second, and tell me why you're changing the number. What does it mean, dominant?
So dominant means if we rearrange this thing, then here 7 is the biggest coefficient, right?
Okay.
And then if we rearrange this, 16 is the biggest coefficient. And then if we rearrange this, 4 is the biggest. So first row has 7, second row has 16, third row has 4. So this is called dominant condition. Then because of this dominant condition, we can remove this thing. We can remove this thing. So I will remove this 5, right? That's all I need to do. This is all I need to do, right? Then everything is diagonally dominant, right? Any questions? Then let's do it. So initially, we will solve the system without any W. So we will solve this system with Gauss-Seidel, right? Just iteration. So take a look. X1 is this one, X2 is. So compare this with the next one. As you can see, it's diagonally dominant. We don't even need more steps. So let's go up a little bit. So where do we have to stop? Almost extremely fast convergent. So 23 is too much, right? So I will reduce the number to some smaller number, like what number? Like it's about 7, right? About 7. So let's do it. Let's do it with 7. Then it's still rough, right? It's still rough. As you can see, it's still rough after 7 iterations. So to get a nice iteration, how many times do we need to do it? So 7 more times, or about 5 more times, right? Then good enough? Very good, right? About, where is the break-even point? About this, right? About this is good enough, right? So about 7 and then 8, 9 times might be enough. About 10 times might be enough, right? 10 times to reach the number. So 10 is the number that you need to iterate to solve this kind of problem. So I will solve it. So this is the starting point, and then we iterate 10 times, right? You iterate 10 times. Then we reach this kind of number, right? We reach this kind of number.
So then when we do it with the SOR.
Right, so let's do SOR. So about 1.2. Still not good. So let's go back and then change the number. What is wrong with this? Did I jump too much? Still, so I guess jumping caused some. So this isn't the exact science. This is, in some sense, trial and error method, trying to find the optimal W value. By experience, we find the optimal value and then use it. For some cases, we have optimal value. So in this case, we should not use big W. Like I used about this number, and it works a little bit better than.
Could you create a loop with a loop of W's and see which one?
We do trial and error to find best W, and then once best W is found, then we use that kind of W all the time for that problem. So as you can see, let's try about 7, and then after this I will stop. So are these good enough? About this point we get 6, right? 6, 8, 6, 8, 6, 8. So as you can see, SOR itself is an exact science. SOR is an exact science.
In your notes, you give a Poisson's equation.
That's right. For that kind of equation with fixed coefficients, right? Like 4, 4, 4, 4. We have nice theoretical numbers. For others, we should try to find the best. And then once best W is found, it could be 1, it could be 1.1, 1.01, or something like that, right? Then that number can be used. So what I mean is, SOR method is the alternative to find the best method. And let's stop here. Next time, I will cover.
Question about the homework.
Mm-hmm.
It says for problem 1, so and equations within unknowns, right? But then when you say implement the algorithm, I is between 1 and n, and j is between 1 and n plus 1. Well,
That 1 plus 1 is right hand side of the equation. Right hand side.
If you have
B, a constant term, right? Yeah, that's right.
Gotcha. It's like this. You're solving a 3-by-3 system, and there's your solution. There's your 2-by-3 side.